Hey Chem students, it's your third installment in your solutions unit. This lesson is going to be all about polarity and solubility. So two main goals for this lesson. First of all, explain the relationship between polarity and solubility, and that wouldn't also include, what polarity is. And secondly, be able to predict whether a particular solute will be able to dissolve in a particular solvent based on a couple things. First of all, this mysterious polarity thing. And second of all, using the solubility rules. Now, you should have gotten a handout that has the solubility rules listed out on one side and a chart on the other side. So if you didn't get that, be sure to get one before you continue on with this video. All right. So again, this is all about polarity, and in order to understand what we're doing going forth, we need to, know what polarity is. Now, in the past, when we've talked about things being polar or nonpolar, we've been using that term to talk about bonds. In particular, if you recall, we use the term polar covalent bonds to describe bonds where two atoms are sharing electrons, but that sharing is uneven. One atom is hogging the electrons more than the other one is, kind of like when you and your friend share pizza and your friend eats 3/4 and you only eat 1/4. Yeah, you shared it, but it wasn't really fair. All right, so we use that term to describe an uneven sharing of electrons between two atoms, whereas we use the term nonpolar to describe a bond where everything is being shared evenly. Both atoms get equal access to those shared electrons. It's more of a fair fight. All right. Now, it turns out we can use this term polar not only to describe bonds, but actually to describe entire molecules, again, based on how electrons are being shared in those molecules. Okay. So first of all, in a polar molecule, just as in a polar bond, what we find is that the molecule is a little lopsided. The electrons tend to spend more time on one side of the molecule than on the other one, again, based on the geometry of the molecule as well as on the electronegativity of the atoms making up that molecule. So our classic example would be water. Again, we've talked about this one before. The oxygen's more electronegative, so our shared electrons spend more time up here where the oxygen is and less time over here where the hydrogen is. So we find an overall kind of negative charge here due to the extra electrons, and an overall kind of positive charge here due to the lack of electrons. Okay. Now, a key thing to know is that all ionic compounds are going to be polar, because again, an ionic compound is just one where there's a huge electronegativity difference between our two atoms. One atom is totally hogging the electrons, and the other atom is basically giving them up. All right, so that means any ionic compound that we've got automatically polar, automatically an uneven distribution of those shared electrons. Okay, whereas we could also have nonpolar molecules, and those are ones that tend to be pretty symmetrical. The electrons are being pretty evenly shared among all the atoms. There isn't one side of the molecule that's way more negative than the other side. And as it turns out, most large molecules, like the ones that make up you and me and the food that we eat, tend to be nonpolar, which we'll talk about more later in the year. Turns out to be, a good thing if this happens. All right. Now, the reason we should care about any of this in our solutions unit, the reason that polarity matters at all, is it turns out that like substances tend to dissolve other like substances based on polarity. So in other words, polar solutes will tend to be soluble in polar solvents, and nonpolar solutes will tend to be soluble in nonpolar solvents. All right, so if I try to mix together two polar substances, they'll tend to dissolve each other pretty well. Or if I try to mix together two nonpolar substances, they'll tend to dissolve in each other pretty well. But if I try to take a polar solute and stick it in a nonpolar solvent, or vice versa, it turns out that doesn't really work very well, and they won't tend to dissolve. And that's what we're going to talk about next. Why does that happen? So here we have an example of two substances that both happen to dissolve very well in each other. The molecule over here on the left in green is an acetate molecule, and the molecule over on the right in red and blue, hopefully you know this one, it's water. If you don't know that, So it turns out acetate dissolves very easily in water. Now the reason for that, if you notice, both of these molecules are polar molecules, okay? Over here in the acetate, the right-hand side has all these oxygens, which are very electronegative, so they tend to have an overall negative charge on them. And what you'll notice is over here we've got our water, which is also polar, and these hydrogens tend to have kind of an overall positive charge on them because all the electrons are hanging over here by the oxygen. And what do we know about a negative and a positive? They tend to attract each other. So what happens when these two molecules get mixed in together is that the negative side of one will kind of find the positive side of the other, and they'll form a weak attraction. It won't be a bond, but it'll be an attraction. And basically what that's going to do for us is facilitate our water molecules and our acetate molecules kind of mixing it up and, you know, interspersing with each other, aka dissolving. Okay, so this is why we find that our polar molecules tend to dissolve in other polar substances. We have this opportunity to form these little electrical attractions between the negative and positive sides of those molecules. Now, a classic example of two things that don't mix together, oil and water. Like the canonical doesn't mix together, doesn't get along thing. So we got some pictures here for these molecules as well. Around the side in the sort of reddish pinkish, we've got our water molecules. And down here in the middle in this black-gray sort of color is a long oil molecule. Right? Now what you notice is, of course, water is polar. We know that already. But the oil, it's all pretty symmetrical. You see that? Like we've got this long carbon chain and then a bunch of hydrogens just hanging off of it. It's all very symmetrical and even. As a result, our oil is non-polar. So we've got a situation with a non-polar solute. We're trying to dissolve it in a polar solvent. This isn't going to work because, again, the water is polar. It's going to want to form those electrical attractions with other polar molecules. So what it comes down to then is the water would rather hang out with other water molecules and get those electrical attractions than hang out with oil, which doesn't really have any positives or negatives. It's just kind of all even all the way through. What makes this sort of sad, if we, you know, totally anthropomorphize our molecules, is that the oil, these hydrogens here, actually are attracted to the oxygens. They sort of want to form those weak intermolecular forces there, but the water's kind of rejecting the oil because it would rather form slightly stronger attractions with other water molecules than with an oil molecule. So the poor oil is left all by itself, wanting to be friends with the water, but it can't because the water would just rather be friends with other waters. Blah. Right? Note that people will often say that oil and water repel each other. Not a true statement, because the oil would like to intersperse with the water. It's just a matter of the water, you know, is rejecting the oil. Oh, I'm all sad now. Okay. So what you've noticed in these past two examples, and probably in a lot of the other solutions that you've run into in your real life, is that the vast majority of the time, the solvent that we're trying to dissolve things into is water. Water is sort of the mother of all solvents. It's the thing that we're always trying to get things to dissolve into, the base of most of our solutions. So, well, there may be times when we're trying to figure out whether something will dissolve in oil or dissolve in, you know, paint thinner or what else. Usually we're interested in seeing if things dissolve in water. Okay. Now, as we've already established, in general, polar molecules will tend to dissolve in water. But as it turns out, water is a little bit picky, and not all polar molecules really quite dissolve in water. And in order to know which ones do, you kind of just have to know some rules. Now, I could obviously give you a whole array of different ionic compounds and be like, dump this in water and see if it dissolves, but that would be boring for you and for me. So let's turn to the scientists who have already figured this stuff out and pull out your solubility rules and solubility chart. Okay? Because those scientists have already dumped all those things into water and seen if they dissolve or not. So, yay for us, saves us a little bit of work. Okay. So if you look at these, at the rules or at the chart, they'll classify all of our ionic compounds as either being soluble or insoluble. And we're always talking about water as our solvent in this case. All right. Now, a soluble salt, aka an aqueous salt, is one that dissolves easily in water. It'll form that nice homogeneous mixture. All of our molecules will get interspersed and we'll just, get a nice, happy solution. And in particular, if you look on the chart on the back, all of our soluble salts are being described as aqueous in that case. They just easily get dissolved into water. Now, an insoluble salt, on the other hand, is classified as being a solid in that chart. And what that means is that that salt does not dissolve well in the water. Its molecules will not intersperse with the water molecules. It'll still form those little chunkies in the water. Remember those? Yeah, that's an insoluble salt, something that will tend to form a precipitate. It won't dissolve in the water nice and easily. Okay. So the last thing I want to do in this lesson is give you a chance to practice using your solubility rules and solubility chart to predict whether particular ionic compounds, aka salts, will dissolve in water or won't dissolve in water. Now, the solubility rules pretty much just lay it out right for you, which cations and which anions tend to dissolve or don't tend to dissolve. Just a little primer on using the chart on the back. Down the left-hand side, what you'll see is a list of cations, metal ions, and on the top of the chart, you will see a list of anions, or non-metal ions. And if you want to find out if a particular ionic compound is soluble or not, you just look for the intersection of the cation in that compound and the anion in that compound, see where they intersect, and it will tell you if it's aqueous, soluble, or solid, insoluble. All right. So I've got 3 different examples for you to try out. What I want you to do is pause the video. That's right. Pause it. I'm not just going to tell you this. You need to think for a moment. Do it. So pause the video, figure out whether each one is going to be soluble or insoluble, and come back to me when you have answers. Alright, if you're listening to this, I'm assuming that means that you paused the video and already figured out whether each thing was soluble or insoluble. If you didn't, shame on you. Alright, first of all, lead-2 iodide. Lead-2 iodide is insoluble. We can figure this out because it tells us in our solubility rules that iodide ions are usually soluble except when they bond with lead-2. In this case, iodide bonded with lead-2, therefore it's not soluble. Next one, ammonium chloride is soluble. It will dissolve in water. And we know this because ammonium ions tend to form soluble salts, chloride ions tend to form soluble salts. Put them together, it's probably going to be a soluble salt. Doesn't say anywhere that it isn't, so we'll just assume that it is. Cool. All right. Last example, iron 3 oxide. Iron 3 oxide is insoluble, will not dissolve in water. We know this because it tells us that oxides tend to be insoluble, and it doesn't say anywhere that iron would be an exception, so it's going to be insoluble. Alright, that's all I have for you guys. Next time we meet, we'll do a little bit more practice with this and get more comfortable with the idea of predicting whether things are soluble and making solutions and stuff. Alright folks, I'm out.